Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 4 of module 9. In the lecture today, we are going to cover the following concepts. First, we will continue with the earthquake moment tensor that we have started in the previous lecture. Today, in the context of moment tensors, we will see the moment tensor in arbitrary coordinate system, and also we will see the relationship between the eigenvectors of the moment tensor and t, p and the null axis. Then we will see how to rotate a moment tensor and what are their characteristics that it will keep intact and what are the different characteristics in the different coordinate system. And finally, we will be talking about isotropic and CLVD moment tensors. And finally, we will be having the summary of today's lecture. Before we even delve into the today's lecture, let's have a recap of what we have learnt in the previous 3 lectures of the module 9. We learnt about the elastic rebound theory that states that the strain accumulated in the rock gets more than the rock that it can withstand, then the slip will happen, which will result in an earthquake. Elastic rebound theory was given by H. Reed, and he stated that the elastic rebound theory happens in 4 stages and phases, the first of which is interseismic stage that consists of long periods between large earthquakes during which elastic strain accumulation occur in the broad region. So interseismic stage made the most of the time among all the 4 stages of the elastic rebound theory. In the pre-seismic stage, the force shocks happens that is associated with the small earthquakes. Then the co-seismic phase comes, which is the phase where the earthquake itself happens with a rapid motion on the fault that generates the seismic waves. In the final stage, that is the post-seismic stage, or you can say post-seismic phase, that occurs after the earthquake, and this is the stage when the aftershocks happens and also the transient after select occurs for a period of years, and then the fault moves back into the interseismic stage. So this is the seismic cycle that elastic rebound theory follows. And then we learnt about the 2 different coordinate system. The one coordinate system was associated with the phi, delta and lambda. Another was n cap and d cap, where n cap is the unit normal vector on the fault plane, d cap is the slip vector or the unit vector along the slip. That basically is useful to describe the fault geometry. The unit normal vector to the fault plane can be represented by n cap, that is equal to this particular matrix, that is minus sine delta sine phi f, sine delta cos phi f cos delta, and the slip unit vector is defined in the slip direction, that is d cap, and it can be represented by this particular matrix. And in case we are talking about the fault geometry, where you have like dip angle, slip angle and the strike angle, then for a pure strike slip fault, so pure strike slip fault, as we have discussed, are of 2 types. One is left lateral strike slip fault, another is the right lateral strike slip fault. So in case of pure right lateral strike slip fault, the lambda will be 180 degree, and in case of left lateral strike slip fault, the lambda will be 0 degree. For a pure dip slip fault, that is again of 2 types. One is normal faulting, when the hanging wall slips downward, and another one is reverse fault or thrust fault, when the hanging wall blocks move upward. So in case of the normal faulting, lambda will be equal to 270 degree, and in case of thrust or the reverse faulting, the lambda will be equal to the 90 degree. Then we learned that seismogram that are recorded at various distances and azimuths, it can be used to find the geometry of a fault during an earthquake, and these are known as focal mechanisms. And it uses the fact that the pattern of radiated seismic waves depend on the fault geometry. Then we talked about the first motions, and first motions can be used to find out the zone of compression and the dilatation. It basically defines the zone of deformation into 4 quadrants, 2 for the compressional and 2 for the dilatational. And these quadrants are separated by nodal planes, which are known as the primary fault plane and the auxiliary plane. So there is some ambiguity in the identification of fault plane and the auxiliary plane. That is because the slip that is happening either along the fault plane or the auxiliary plane will produce the same 2 compressional and the 2 dilatational zones. So we need some additional information from additional data sets, such as the geodetic data, or maybe from the geology of an area, or maybe by looking at the pattern of the aftershocks. The elastic radiations can be described as resulting from double couple of forces, and these forces are known as equivalent body forces. So if you remember, we have seen some irregular surface on which some forces are occurring along the fault plane, and we can equivalently define a rectangular block and can define the equivalent slip along the fault that is equivalent to the slip that is happening on the elemental area on the shape of the irregular shaped body. And then we can define its area, that may be the equivalent area to the area of this irregular shaped body, and that may be having the width W and the length L. And then we can define the forces that is equivalent to all the forces that are acting on this particular irregular shaped body. So the elastic radiations can be described as resulting from the double couple of forces. These forces are known as equivalent body forces for the fault slip. The radiation pattern we learnt about for the P wave and the S wave can be given by these expressions, that is the amplitude in the radial direction, that is for the P wave, which is equal to 1 by 4 pi rho alpha cube r, that is basically proportional to the inverse of 1 by r. And there is this seismic rate movement function, that is m dot, having the t minus r by alpha, and this is what it represents the radiation pattern of the P wave. Similarly for S wave, we have u theta component and the u phi component. So u theta component having this amplitude term, then this is seismic rate movement function, there you have the radiation pattern. Similarly for u phi, you have the same amplitude term, and this is the seismic rate movement function, and here you have the radiation pattern. Then in the last lecture, we learnt about the seismic movement tensor that can be used to give the complementary insight into the rupture process and can greatly simplify the seismogram inversion to estimate the source characteristics or source parameter. So seismic movement tensor can be used to find out the geometry of a fault and its source parameters. We assume the equivalent body forces which produces the same radiation pattern as the slip on the fault for the earthquake and the other seismic sources. The seismic sources can be modeled as either single forces, force couples and the double couple. And in the previous class we learned that the single forces are the single force, something like this. This is like in x direction. And if you have another force associated with it, then it will be known as the force couple. It can be having an offset either in the y direction, x direction and the z direction, and the orientation of the force also can be different. And in case you have the double couple, then you will be having another couple associated with it, something like this. So it will be known as, these are having the offset between the forces in this double couple system. The components of the movement sensor represents the fault geometry and size of the earthquake represented by a scalar movement, that is the m naught, and this m naught is equal to mu ds, where mu is the shear modulus, d is the slip and S is the area of the fault. Moment tensor like stress and strain are symmetric in nature. That means Mij will be equal to Mji. So that means that they will be having symmetric in nature, so that you can keep the net torque 0, and there will be a set of axes which will make off diagonal elements 0. It is similar to the stress and strain tensors. Then we learnt about the Green's function. If you remember, we defined a term capital G, and which was having x comma t for a given x naught comma t naught, and this basically is used to denote the path effect through which the seismic waves have travelled. So when you will couple it with the impulsive force such as f x naught comma t naught, in the previous class we took the example of the delta function. So if it is coupled with the body force f x naught comma t naught, then combinedly it will represent the deformation at a point on the surface of the earth, or you can say the displacement at a point on the surface of the earth. And these displacements are linear in nature. Either you have forces at a point in this direction, another force in this direction, another force in this direction. So you can sum those up and then have a product individually through which the waves have travelled with the Green's function. Then it can relate it to the net deformation happening at the surface of the earth, or the net displacement. The moment tensor we have learnt about. It can be rotated into its principal axis, such as the pressure axis, tension axis, and its null directions. And moment tensor is an array of 9 double couples. So this is for the M11, this is for M12, M13. So this is basically representing the couples that is basically having the offset into the x1 direction, and this is having the offset in x2 direction, and this is having the offset in x3 direction. So Mij, where I is the direction of the couple and J is the offset of the force couple, and M0, that is the scalar moment, can be defined as the product of the shear modulus mu and then with the slip and then the area, that is represented by capital A. The seismic moment, or you can say scalar moment, can also be written in this form, in the form of the component of the moment tensor 1 by under root 2 in bracket sigma ij m ij square to the power under root. The moment tensor, since it has 9 components, can be represented by this particular tensor. So it has 9 components. So these are the diagonal element and others are the off diagonal elements. Let's start with the lecture today, and we have seen that the seismic moment tensor M, that has the 9 force couple, can be represented by the equivalent body forces for seismic sources of different geometries. So in the XYZ coordinate system, the moment tensor can be represented by this, and if you want to rotate it such that in another orthogonal coordinate system, so that you can have its simplified version and it can represent the earthquake as a source, then it can be written something like this, and where you will be having the M0 for the M21 and this is for M12. This is, if you take M0 common, that is the scalar moment, then it will become something like this. And the components of the scalar moment and the components of the unit vector that is perpendicular to the fault plane, and d cap, that is the unit vector along the slip of the fault, can be represented in this format, where M0 is the scalar moment, Ni dj plus Nj di, and in the expanded form, in the form of the tensor, it can be written something like this. And this particular thing says that if you can interchange N with D, then because the tensor is symmetric in nature, so if you are interchanging N and D, then the tensor will become symmetric in nature and Mij will be becoming equal to Mji. So basically these terms will be equal to each other. Likewise, this term will also be equal to each other. Likewise, there are other terms as well. So the interchangeability of n cap and d cap makes the tensor symmetric. That means Mij is equal to Mji. Physically, this shows that the slip on either the fault plane or the auxiliary plane yields the same seismic radiation pattern. So because as I was talking about the ambiguity, though you can say that if the slip either is happening on the fault plane or the auxiliary plane, it will produce the same radiation pattern from the fault. The trace of the moment tensor, it is similar to the stress and strain. The trace of the tensor is 0. So you can say that the sum of the diagonal element will be 0. And this means that sigma I MII is equal to 2 m naught NIDI, 2 m naught n cap dot d cap will be equal to 0. So since if suppose the slip is happening on the fault plane, obviously it will be happening on the fault plane, then the perpendicular to the normal will always be equal to 0, which means that the moment tensors corresponding to the slip on the fault have 0 trace. That means the trace will always be equal to 0 if the slip is happening on the fault plane. A non-zero trace implies a volume change. That means if the sum of the diagonal element is non-zero, that basically happens in the case of explosion and the implosion, which means that these are the isotropic component, and for such an isotropic component does not exist for a pure double couple sources. The scalar moment gives the magnitude of the moment tensor, which is analogous to the magnitude of a vector, and it can be given by this expression. Now let's talk about how the eigenvectors of moment tensor are related to the tension, pressure and the null axis. And as we know that the vectors can be represented in the orthogonal direction coordinate system, that are t, p and the b, and tp and small t and small p and the small b are the unit vectors, and these can be identified using these expressions. So t is n cap plus d hat, and p is the n cap minus d cap, and b cap is the cross product of n cap and the d cap. That means b cap will be orthogonal to both n unit vector and the d unit vector. The eigenvectors of the moment tensors are parallel to the t, p and the null axis. So basically you are going to find out the principal axis of the moment tensor, and those will be representing the eigenvectors of the moment tensor, and those will be parallel to the t, p and the null axis. As with all tensors, the moment tensors also can be rotated using a transformation matrix, and the useful notation is the one where we orient the axis into the pressure and the tension axis of a coordinate system. And let's suppose you have this particular moment tensor and you want to rotate it into its principal coordinate system pt axis. So in that case you can have the t as n cap plus d cap, small p as n cap minus d cap, and b cap is n cap cross d cap. And when we are transforming it into the principal axis coordinate system, then you can do the operations something like this. Then you will get your moment tensor rotated into its principal axis coordinate system. The trace will still be 0. That means it is unchanged. That means the trace, that is the sum of the diagonal element, which is not changed by an orthogonal transformation. So you can see in this case also the sum is 0. So the trace which is not changed in an orthogonal transformation started as 0, and sum is still 0, remain 0. So the isotropic component is an invariant of the moment tensor and does not depend upon the transformation system or the coordinate system. Even if you are rotating, then also your trace will remain 0. In the transformation itself, the physical movement of the tensor will also stay the same. That means the two different looking force system in the principal axis or in the original coordinate system will always remain same. The physical movement will remain always same. That means both of the system will give you the same radiated seismic waves. Let's talk about two type of moment tensor. One is the isotropic moment tensor, another is the CLVD moment tensor. So CLVD stands for compensated linear vector dipoles, and in the case of isotropic, so for the isotropic moment tensor, all three diagonal terms of the moment tensors are non-zero and equal. That means the polarity of the first motion will be same in all the direction. So in all the direction the polarity will remain same. So if you remember, we talked about the compressional zone, dilatation zone. In the compressional we were having the first motion as a positive amplitude and the first motion as negative amplitude in the dilatation condition. So in the case of isotropic source, the first motion will remain same in all the direction. Either it will be negative or it will be positive. It has three vector dipole of three equal and the orthogonal force couple. So this can be produced by explosion and implosion. So in the case of explosion, so this is the diagrammatic representation of the explosion. So the forces that it is producing are going into the outward direction like this. And in the, so as I said, it is a triple vector dipole of three equal and the orthogonal force couple. So this is this. You can see these are the three dipole system, and the moment tensor will look something like this. So you can see the diagonal elements. These are the diagonal elements here. All are non-zero and all are equal. Because it is positive, that means it is indicating that the forces are going in the outward direction like this. And in case of implosion, what will happen? The force will go in the inward direction like this. Okay, so in that case, what will happen in the implosion? All the diagonal elements will become negative. Now, a moment tensor with a non-zero isotropic component represent a volume change, and in this case the volume is also changing in the case of implosion, in the case of explosion, because the trace is non-zero. The meteorite impact could also be regarded as explosive sources. An explosion involves a sudden increase in the pressure which causes non-linear deformation that can melt and even vaporize rocks. As this shock wave of pressure expands, its amplitude decreases until the deformations are small enough to occur elastically, yielding a spherical P wave. If you look at these, some of the selected moment tensor and their associated focal mechanism, the first row, this one, is representing the explosion and the implosion. The left one, this one, is representing the explosion, and on the other hand this one is representing the implosion. So you can see in the case of explosion, this is the moment tensor here, and in the moment tensor the diagonal elements all are positive and equal and non-zero. So these are for the isotropic source, and this is also for the isotropic force in the case of implosion as well. You can see there is a negative here, and that is basically indicating towards the triple dipole is consisting of the forces, those are coming in the inward direction, and this is for, these are all negative here. And the other things that are here are basically for the double couple sources, like this one is for the right lateral strike slip fault, this one is for the left lateral strike slip fault. Similarly, others are for the normal and the reverse faults. Here you can see this is the difference in the waveforms of the artificial source such as explosion, maybe if you are having through some nuclear test, and the natural earthquake. So this is from the natural earthquake, this is the effect of on the seismic waves due to the explosion, and this is the natural earthquake. If you compare both of them, then you will see the P wave energy is very large. There is a spike, very large spike, and very large P wave energy. And in case of earthquakes, the large P wave are not there. But on the other hand, surface waves are very large here, but in case of the explosion, the surface waves are comparatively small. Now let's talk about another type of moment tensor that is known as compensated linear vector dipoles. In short, these are known as CLVDs. These are a set of 3-force dipole that are compensated with one couple and -2 times the magnitude of the others. So that means, let's look at this particular moment tensor here. You can see that on the diagonal part you have this minus lambda, which is the negative 2 times of the other two. That means lambda by 2 and lambda by 2, and this basically known as the CLVD, compensated linear vector dipole. If you have any other moment tensor, something similar to this, where the diagonal elements are having the property such that the one dipole is the negative 2 times the magnitude of the other two, then you can say that that is a compensated linear vector dipole. The examples are these. These are the examples. You can see that there is this one which is having the negative 2 times of the other two, and here also this is negative 2 times of the other two. So you can see in this case also, like this is the force in the x3 direction, this is in x2 direction, but in the x1 direction the force is double negative and acting in the opposite direction of the other two forces. Those are in x2 and x3 direction. Similarly, for this case also you can see the same thing, and this is also here. So the trace of the moment tensor is 0, so there is no isotropic component. And this is the summary of today's lecture. We will continue with CLVD in the next lecture. Symmetry property of the moment tensor shows that slip on either the fault plane or the auxiliary plane yields the same seismic radiation pattern. So we have said that, we have shown that the symmetric property, the symmetry means like Mij is equal to Mji. That basically shows that the slip either on the fault plane or the auxiliary plane yield the same seismic radiation pattern. So there will be an ambiguity where the slip is actually happening, but moment tensor actually follow the property of symmetry, which is similar to the stress and strain, and it says that the slip either is happening on the fault plane or may be happening in the auxiliary plane, and that yields the same seismic radiation pattern. Either it is on the auxiliary plane or to the fault plane. The trace, that means that is sum of the diagonal element of the moment tensor, is 0. That means sigma Mii will be equal to 2m naught Ni di, n is the unit vector in the fault plane, and d is the unit vector along the slip direction, and that will be equal to 0. The scalar moment, which is represented by this, the scalar moment gives the magnitude of the moment tensor, which is analogous to the magnitude of a vector. Thus, the eigenvectors of the moment tensors are parallel to the tension axis, pressure axis, and the null axis. The transformation, the rotation that we were talking about, the transformation changes the component, but the physical moment stays the same. So these two different looking force systems gives the same radiated seismic waves. So either you have the original coordinate system or you have the transformed coordinate system. In both the system, the physical movement of the tensor will remain same. That means the radiated waves pattern will also be same in both the coordinate system. It will remain intact. For isotropic moment tensor, the diagonal term are non-zero and are equal. So for example, this one you can see these are non-zero and are all equal. These are isotropic moment tensor. And in that case, the first motion will be same in all the direction. So the polarity of the first motion, the focal mechanism is the same in all direction. The moment tensor with a non-zero isotropic component remain a volume change, The compensated linear vector dipoles, in short, these are known as CLVDs. These have the three set of the force dipoles that are compensated. That means with one dipole is the negative 2 times the magnitude of the others. So for example, if you will look at this one, the force that is acting on the x3 direction in x2 direction are having almost negative half of the value of the third direction force. Okay, so you can see this is minus lambda, that is almost negative 2 times of the other two, and this is known as CLVD. So these are the references for today's lecture, and then we will be continuing with CLVDs in the next lecture, and we will also see the interpretations of the moment tensor in the next lecture. Thank you so much. Bye bye.